So homework 4 is due today. We're going to have a quiz on homework 4 on Wednesday. Also, there's a couple of other announcements. There's a shift meeting today, 2:30 p.m. in Building 9257. If you are in a calculus class at 12:45 today, please announce that to your classmates in your class, okay, to make sure that we have good attendance at today's meeting. And those of you who are applying for the NSF scholarship, today at 5 p.m. is the deadline to submit all your documents. And please remind your recommender to submit the recommendation letter also by today. Test 1 results were mixed. In general, it's not as good as I want it to be. The high is 99, low is 45, mean is 70.7, median is 72.2. You all know the difference between mean and median, right? Mean or the average is just sum of all of the scores divided by the number of students. The median is what? Arrange them from highest to lowest. The middle person got a 72.2. That's not STD. Standard deviation is 16.8. It's a measure of how the class is spread out. Let's see. As I said in my email, if you didn't do very well, don't be discouraged. We are dropping the lowest test, provided they're taking the final. So if you didn't do well on this test, most probably you have to take the final. Okay, so I'm gonna share my desktop. Are there any questions on the homework that's due today? No questions. Good, because we're slightly behind. Okay, so let's finish off lecture 4. We were looking at this this problem here, where block B is sliding down relative to A. Okay, and we're asked to find the acceleration of the wedge A and the relative acceleration of the block relative to the wedge. And when we first started looking at the free body diagram, okay, one common mistake that stood when I gave a problem similar to this was to assume that the acceleration of the block was along 30 degrees. That's not correct. Okay, the 30 degrees is only if what? A is not moving, then it's going to move along 30 degrees. In this case, A is going to move to the right. Yes, because the only horizontal force in the free body diagram of A is to the right. Therefore, it's going to accelerate to the right, which means that the absolute acceleration of B relative to the ground is at an angle steeper than 30 degrees. Okay, what you see as the 30-degree vector is only relative to A. And putting 30 degrees here is equivalent to putting the relative acceleration of B with respect to A, and A in this case is a non-inertial frame according to Newton. F equals ma only applies if all your accelerations are with respect to an inertial frame, something that is not rotating or accelerating. Okay, so what that means is for this free body diagram of B, we have normal force plus on the right side two unknowns, magnitude and direction of the acceleration of B. Okay, and consulting with Dr. Phil tells us that this is an unhappy system, 3 unknowns, 1 force and acceleration, magnitude and direction in only 2 equations. And then we looked at the free body diagram of A, and how many unknowns do we have? Normal force and normal force P, and the acceleration of A. It also has 3 unknowns. We tried to do an eharmony.com. We matched them together and see they're happy together, meaning let's look at the total number of unknowns in all of the free body diagrams we have. How many? 5. Okay. In only 4. So even after putting the 2 together, we still have too many unknowns than equations available. Therefore, it's an unhappy system. And the reason why this is the case is because there's a piece of information that we have not used so far. The fact that the acceleration of B relative to A is, yes, it's an unknown magnitude, but it has to be along 30 degrees. Okay? So how do we use that piece of information? So we can use this to relate AA and AB, because the acceleration of B is equal to, from your relative acceleration equation, is the acceleration of A plus the acceleration of B relative to A. You okay with that? Okay, the acceleration of B, as we see here, actually has two unknowns. Both its magnitude and its angle are unknown. We only know that it's got to be steeper than 30 degrees. Okay, must be equal to acceleration of A. It's also unknown, but it has to be horizontally to the right. Okay, plus acceleration of B relative to A, also unknown magnitude, but it has to be along 30 degrees. Yes. So in terms of number of unknowns here, A sub B has two unknowns, its magnitude and its direction. If we replace A sub B by the sum of AA and acceleration of B relative to A, it's still two unknowns, right? Magnitude of AA and magnitude of B relative to A. The only difference is one of those unknowns, AA, is exactly the same unknown in the FBD of A. You see that? Which means that individually this would be unhappy, this would be unhappy, but together they will be happy because instead of having 5 unknowns, we'll only have 4. You agree? So if I represent this in terms of a vector equation, what this tells me is the acceleration of B, which is unknown magnitude, unknown direction, right, is equal to the rightward acceleration of A, right, plus an unknown magnitude acceleration of B relative to A, but it has to be along 30 degrees. You see this triangle? So what I'm going to do is, I'm going to multiply this triangle by the mass of B and represent that triangle in the free body diagram of B. So instead of representing MB times A sub B, I'm going to replace that with a sum of two vectors. A horizontal, mass of B times acceleration of B, yes, and another unknown vector, mass of B times acceleration of B relative to A, unknown in magnitude, but in direction, it's 30 degrees. Are you okay with what I did here? Instead of showing mass of B times acceleration of B of unknown magnitude and direction, I'm going to replace this red vector with the sum of the two blue vectors. Okay, and the reason for that is if I do another consultation with Dr. Phil, what are our new unknowns now? What are our unknowns? It's going to be still the normal force on the left, still two unknowns on the right, but the two unknowns are A sub A and A sub B relative to A. Yes? Remember, I am not looking at the red anymore. I'm looking at the sum of the two blue ones, and the two unknowns are unknown magnitude of A, right? This should be A, right? Does that look like A? No, it doesn't look like A. It has to be AA, yes? Can't believe you didn't point that out to me. What are we talking about today? STDs and AA. That's not a good sign. Are you okay with how I'm replacing the red one with the blue one? Because acceleration of B is equal to acceleration of A plus acceleration of B relative to A. So the three unknowns here are now N, AA, and acceleration of B relative to A. And we notice now that although individually SBD of B and SBD of A are still unhappy, we see that this normal force and this acceleration, AA, are the same unknowns, normal force here, and acceleration of, oops, where is it? Right here. Where's the normal force? And acceleration, AA here. Yes? So how many unknowns do we have now, all in all? N, AA, AB relative to A, and B. You see that? So all the individuals, they're still unhappy. eHarmony.com actually makes the whole system happy with 4 unknowns now. So our latest tally is we have four unknowns. And what are the four unknowns now? If we have it this way, the normal force N, acceleration of A, acceleration of B relative to A, and then all these three are coming from the FBD of B. What is the only additional unknown from the FBD of A? Huh? It's P, right? Yes. P is some panormal force. It's a panormal force exerted by the ground on A, right? Or it could be silent P as in psychology or in pneumonia. Normal force. Okay? I don't want to call it N because it's not going to be the same magnitude. Yes. But there is contact between the ground and A, so there must be A. Okay? Say that again? Not necessarily. So that's the dangerous thing, okay? So a dangerous thing is some of you will say, oh, the total normal force coming from the ground is just the sum of the two weights. And that's not true. Because, what? There's motion now. You're again in your head saying that the summation of forces along the vertical is 0 for the FBD of the two. And that's not correct because B actually has a net downward acceleration. So there are certain things that you sort of have to unlearn from physics, right? That attention is equal to mg. That's not true anymore when you're moving. In the same way here, okay, if nothing's moving, you're correct. Because the summation of force is vertical for the FBD of the two. The only external force is weight of B, weight of A, nothing else. The only external vertical force is the normal force. The normal force is balanced. But in this case, the summation of force is vertical for the two combined. It's not 0 because they're moving. Yes? No. No. Okay, so that's another dangerous thing. Just because it's not moving yet, because velocity is 0, doesn't mean that the acceleration is 0. The acceleration is still 0. It's just starting to change its velocity. No, because motion of B is not along 30 degrees. Right? So what you want to do is just look at this, forget what you sort of have conceptual understanding of in physics. Just look at those equations and say that any equation I'm going to write would be based on these free body diagrams I know I will be. Okay? So I agree with you that there's no net moment. It's not true along any direction, because if you go along 30 degrees, B has a component of motion along 30 degrees because it's not really along 30, it's along 30. And also now A also is moving perpendicular to 30 degrees. So just try not to visualize so much, okay? And just say these two diagrams are correct. I will just base any equation I write on these diagrams. Okay? So having a happy system now, because we have 4 equations, Dr. Phil's diagnosis will be, yes, you're happy. Okay? And from this point on, everything will just be vector algebra, right? Set up the 2 equations here, set up the 2 equations there. It doesn't matter how you do it, and you'll have 4 equations and 4 unknowns. So let's look at that. From the FBD of B, okay, what are the 2 equations I can set up? So I'm not even going to try rotation, because along any direction, okay, I will have at least 2 unknowns. You agree? You usually do perpendicular and parallel to n when you want to avoid an unknown, right? But if you go to parallel to the incline, this 2 will still enter anyway. Yes?
So I'm having a little bit of confusion of seeing how we can say that block A is also moving.
Look at this diagram. Okay? We know that it's not moving along the vertical. Yes. Okay? Look at this diagram. Is there a net force along the horizontal? Just look at the free body diagram. Is there a net force along the horizontal? Yes. In what direction is the horizontal? To the right. And that rightward component of the normal will give rise to this. Yes, as I told you, look at your P-body diagram. If it's correct, it will tell you what's happening. So you may want to use less of your intuition. Okay, just look at the diagrams. The diagrams, if they're correct, they don't lie. Okay, so the two equations are, I'm gonna do what? For B, maybe one summation forces along Y equals the summation of effective forces along Y. I'm not gonna say it's what's this? 0 or mass times acceleration. I'll just look at that both sides of the diagram. So along Y, what did I do Y first? I don't know. So what would I have along Y? It's minus 12, right? Plus the normal force times the sine of, what is that angle? 30 degrees, right? So it's going to be sine of 60 degrees. Are you okay with that? Because the normal force is perpendicular to the incline, therefore that angle there is 60. Yes? What's B equal to on the right side? What do I see as vectors on the right side? Now for the right side, I'm not looking at the red one. I'm looking at the sum of the two blue ones. Yes? So I will look at the Y component of MBAA, nothing, because it's completely horizontal. Plus the Y component of that, which is A minus what? MB times the sine of the unknown acceleration of B relative to A. Whoops. Don't report me to your trick teacher, okay? Oops. My pen is stuck. Uh-oh. What's happening? So it would be minus MB, acceleration of B relative to A, sine of 30 degrees. Yes, I'm just looking at the vertical component of my pen got stuck, and it's the weather. It's too hot. Blame it all on global warming. Yeah, it's completely frozen. No, class is canceled. Yeah. So, and then along X, okay, what would be your equation? Along X, you will have no component from the weight, right? And there will be a minus n cosine 60 because it's to the left. Must be equal to, on the right side, you're going to have MBAA to the right, and then the horizontal component of MB, acceleration of B relative to A, cosine 30 degrees. Right? So, and then everything will be, so it's a new battery. I think I just replaced this battery recently. Okay. Oh yeah, it's working now. It was the battery. So acceleration of B relative to A times the, what's this, sine 30 degrees. And then along the horizontal, summation forces along X equals summation of effective forces along X would give me, what, minus n cosine 60. Okay, must be equal to MV times AA. Do you understand where I'm getting that? Okay, so for the forces along X, it's only N. That is a horizontal component to the left. And then I have MBAA, completely horizontal, minus the leftward component of MB, acceleration of B relative to A, cosine 30 degrees. Okay, so I could call this equation 1, this is equation 2. For the FBD of A, I will use, I don't even have to go along Y, right? Because P is not even being asked in the problem, yes? So I'll just go along X equals summation of effective forces along X. So what do I have here for X? It will be a positive N, that's the only N cosine 60 to the right, must be equal to, what do we have on the right side? Will be mass of A times acceleration of A. You okay with that? Yes? The only horizontal components coming from N, cosine 60, MAAA. And I don't even need to do the Y, because if I look at my equations, 1, 2, and 3, right? You just need to solve simultaneously for, we have 3 unknowns here, right? And A, and acceleration of B relative to A. P doesn't even need to be involved in the problem. Okay? So, big picture, acceleration of B is not along 30. It's only the relative. Okay? And then, the key to the solution is, in order to use the fact that the relative acceleration of B relative to A is, although a known magnitude but known direction of 30, we replace the AB with the vector sum of AA plus acceleration of B relative to A. Moody's favorite topic, right? Relative acceleration. Okay? So I'll leave out the details of the algebra and go, we're slightly behind, so I'm going to go here now for curvilinear motion. Because one of, I think some of the homework problems already had curvilinear motion in them. So the idea is, if you have an object in curvilinear motion, okay, Newton's second law still applies, okay, and on the right side here, if it's in curvilinear motion, your acceleration vector could be expressed in different components depending on your choice. Right? What are the 3 systems for curvilinear motion that we've looked at? Okay, that's the second one, normal tangential. What's the first one? Rectangular, or Cartesian, AX and Y. And the third one is radial and transverse. And how do you decide which one to use? Yes, if you're given the radius or interested in the radius of curvature, use normal and tangential. If what's happening along X is sort of independent from what's happening along Y, you use rectangular. If you have something rotating and the length changing, it has to be radial and transverse. Okay. So in each case, though, you will have, if it's 2-dimensional motion, you'll have 2 equations, right? So for horizontal component, okay. Oh, if it's in 3D, you just do a summation of forces X, Y, Z independent of each other, right? Those are your 3 equations. In your normal and transverse, normal and tangential, what do? Your acceleration now is resolved into its 2 components, tangential and normal. Therefore, you'll have 2 independent equations. So equations would be what? Summation of forces in the tangential direction equals mass times tangential acceleration. Summation of forces normal equals mass times acceleration normal. And of course, we know that a tangential is what? dv dt, the rate of change of the speed with respect to time. And the normal acceleration is v squared over rho. And again, if you've forgotten, a tangential represents the rate of change in the magnitude of the velocity, and a sub n represents the change in the direction of the velocity vector. Now, for radial and, oops, there's no radial and transverse. We'll have to wait. There was no radial and transverse on the homework, right? Yeah, that's probably right. So, here's an example. Packages each of mass m are delivered from a conveyor belt to a smooth circular ramp with a velocity of v0, 1 meter per second. So these packages here are delivered onto this ramp with an initial velocity v0 horizontally, and then we're asked to find the angle theta max at which the package begins to leave the surface. So initially, it's going to get deposited here with an initial velocity rightward of v0, right? So it's going to slide to the right, but as it slides to the right, what happens to the speed? It's going to increase because what? Gravity is accelerating it. Okay? So that eventually, if v, remember what happens here? What's the effect of increasing velocity? Increasing the speed, okay, can either what? Increases the increases the centrifugal force. Let's not talk about centrifugal force. It increases the normal acceleration, right? If I increase V on the right side, it either increases the normal component, or for the same normal component, what will happen to rho if I continue increasing V? Yeah, it will increase. It has to increase the radius of curvature, right? Okay. I think increase. I said if you increase V and keep AN the same, rho has to increase also. Yes. And increasing the radius of curvature means that it's no longer along a circle. Right? So there will be a point wherein what the speed is so large such that it cannot keep its radius of curvature of 0.5 meters. It has to fly off to a new radius of curvature that's bigger than that. Okay, and we're looking for that. So if we say that that's some theta max over here, okay, we're looking for that theta max at which what can we say? The velocity corresponds to, it's not the maximum velocity, but it's the velocity at theta. What do we call it? Velocity at escape velocity. So I like that. Let's just say it's the velocity at theta max. Okay. So any suggestions on how to find this theta max at which the object leaves the ramp? Yes, Nick. Okay, so before we separate acceleration vectors, we have to show an acceleration. And how do we show an acceleration? Okay, so we'll do an FBD. At what position? Okay, let's try what happens at theta max. Okay, and look at the free body diagram on the left must be equivalent to the effective force diagram. Yes? So what do I need to show on the left side? What are the forces acting on the block? Okay, gravity. So I'm going to call it mg. I wasn't given what m is, but I'm going to represent as mg. What else? Okay, so they're saying normal. Okay. Oh, he's saying zero normal. Why is zero normal? Okay, so you guys are too advanced. He's saying that at the instant that theta equals theta max, the normal force will approach a value of 0. Is everyone agree with that? Why? Yes, if it's ready to fly off the ramp, it's ready to lose contact with the ramp, right? That means n is approaching 0. If n is not approaching a value of 0, what does that mean? It can still continue moving without leaving the ramp. So leaving the ramp requires loss of contact, and to lose contact, the normal force will first have to go to 0. Yes? So that's a good observation. You guys are good. Must be equal to, and this is what Nick was saying. What do? We're going to have two components of acceleration. One called mass times acceleration tangential, right? You agree that the tangential is tangent to the ramp, and mass times acceleration normal. Which, by the way, is, what is this equal to? Oops. Is it mass times acceleration normal 0? Why is it 0? The normal force is 0, right? But what constitutes the normal acceleration? Oh yeah, as long as it has speed, that's not 0, right? And as long as it's not along a straight line, and I don't think it's going to move along a straight line, because even after it loses contact, it will actually move along a parabola according to projectile motion, right? So this is not 0. 0 normal force doesn't mean that the normal acceleration is 0. Okay, because number one, it's moving. V is not 0. And number two, it's not moving on a straight line. So rho is not infinite. Okay? So, how many unknowns do we have for this diagram? So I'm consulting with Dr. So unknowns with Dr. Phil now. What are the unknowns that can you... So on the left side, do we have any unknown on the left side? It's the max, right? We don't know where this happens, right? Where this happens, we know that the normal force is 0, so the normal force is no longer known. But the position theta max where this happens is unknown. What do I have on the right side as unknowns? The V, which is actually V theta max, right, is unknown. And the acceleration tangential, yes? Right? So I'm counting V theta max as the same as unknown as A sub n, right? Whether I call it A sub n is unknown or V is unknown, it's one unknown, right? I still know what rho is, right? It's only about to lose contact with the ramp, therefore the rho is still trying to change from 0.5 meters, the radius of the ramp. It's probably going to cancel out. Because any value you have here will have an m. It will probably, what that means is it doesn't really matter how heavy that thing is, it's going to fly up at the same angle. Okay? But this is unhappy, yes? Okay? So any suggestions? Any other suggestions? Constant. Oh, here's one suggestion. I will announce this. I won't tell who I suggest. Is to use what? Constant acceleration equation, and basically, or back of the calculator equation, in order to find what? V theta max, because you're given the initial velocity. Was that you're going to suggest? Similar. Ooh. So their reasoning is there's only one force acting on the object, which is gravity, and gravity is a constant, therefore the acceleration is constant. Correct. It's only after it has lost contact that n is no longer acting, right? Right? All from the beginning, when it's at the initial position to right before theta max, gravity is not the only force that's acting. The normal force is also acting, and you will agree that that normal force is changing because it changed from, not only is the magnitude changing, don't even think about this, the direction changes, right? So even if the magnitude of n doesn't change, which we know is not true, right? The fact that the direction is changing already nullifies your assumption that all the forces are constant. Therefore, the constant acceleration equation is not valid. Yes? So what do we do, Nick? But that equation is going to come from this free body diagram, basically.
From the left-hand side?
Yes, but I'm already counting those from the two equations, right? This will, expressing the x and y components or normal and tangential component of this does not make the system happy, right? We cannot what? Okay, so he's suggesting write an equation for the normal force and take some kind of a limit so that it goes to 0 at some position. So where are we going to get that equation from? So yes, I agree that sounds like a good idea, but where are we going to get that equation from? What equation will give us some, he's saying that yes, n is not 0 all the time. So why don't we try to come up with an expression that has n in it, that's not necessarily 0, but some kind of n that depends on theta, and then use some limit. That's not true. That's not true. The n is changing, and n has a horizontal component. So yes, it's related to the height. Yes, yes, Jose.
Can you do a free body diagram when you study?
Oops, can we do a free body diagram? You were getting warm there. I was getting excited. So he said, do a free body diagram when it started. Okay, and what would that give us?
Will there be a normal acceleration that's not actually?
Yes, but that normal acceleration is also changing, because that normal acceleration is gonna depend on the value of n, right? So he's getting. Let's combine the two suggestions. So Jose is suggesting we look at another free body diagram, but it would not be sufficient to just look at it at the initial position, because it will not relate to any of the things that are unknown here: theta max, v theta max, and a tangential at the final position. Right? And let's relate that to the next suggestion. Let's look at the normal force at some arbitrary location. And my question is, where can you see a normal force from a free body diagram? So I think a good idea is to look at what? FBD at some arbitrary theta. Not necessarily at the beginning, not necessarily at the end, but some variable theta, so that we can see if we can apply some kind of limit or constraint that Nick was saying. Does that sound like a plan? Okay, go. So at any theta, what are the forces acting on the free body diagram? So let's see. So here's some smaller theta here. That's the FBD, and here's the. Okay, what forces are acting? mg is always there, and then we have a normal force. Okay? And the normal force this time is not 0, right? Because it's something between, so this arbitrary theta here is between 0 and theta max, right? In fact, I'm gonna remove the equal sign, yes? Somewhere in between the two variable, okay? So are you happy with my FBD? There are only two forces acting. Okay, the difference between this position and the theta max is a theta max n goes to 0 here, and it's not 0. Okay, must be equal to, on the right side, we're going to have what? Mass times A tangential. By the way, the value of this A tangential here, again, is in general different from the A tangential here. Okay, because it depends on the position, and some mass times A normal, which is going to be mass times some V squared over rho, right? And like this V is V at theta max. Are you okay with this? Yes, the normal force is always towards the center of curvature of the path, which is the center of the circular arc. Okay? Yes? Yes, the normal acceleration is towards the center of the arc, and the normal force n is away from the center of the arc. Okay? So, will this give us anything that's useful in terms of, what equation are we looking for here? We need another equation that relates maybe two or all three of these. Yes? So how do we do that? Okay, so he's saying integrate. What are we going to integrate? So, okay, we're getting really, really warm. So what's our separable differential equation? So we need a relationship between V, theta, and A tangential, but what's a tangential? Is dv dt, right? So we really need a relationship between theta, v, that's it, right? Because a tangential is also related to theta. And where do we get that? Oops, you too, then. Okay, let's forget we heard that. So, in this relationship that we want, I don't want n involved. Correct? Maybe? Because I'm working off of this unhappy system. I just want theta, v, and at involved. And at itself has v in it. Right? So I will avoid the normal direction. I will do a summation of forces in the tangential. Why? Because the normal equation will involve the n, and I'm not really interested in n. I'm not saying it's a bad equation. We just don't need it at this point because we're working off of trying to relate theta max, v theta max, and a tangential. So what would be my f tangential? I'm going to have an mg positive sine theta. Are you okay? What's sine? Yes. This angle here is theta relative to the vertical, and the component of that in the tangential direction, which is this, is a sine. Must be equal to, what do we see on the right side? Just mass times a tangential, because a normal is perpendicular to the tangent. So good that m cancels, but it's g sine theta equals, what's a tangential? dv dt, and we're getting closer to next separable differential equation, although right now I have a little bit of a problem. Is this a separable differential equation? It has three variables in it, right? Theta, v, and dt, right? And t, right? So which one of the three, which two of the three should we keep? V and theta, right? Keeping in mind what we're trying to get here, V and theta. So I need to eliminate t. How do I eliminate t? So I can write this as what? dv ds, right? Times ds dt. Are you okay with that? Okay, why am I using s? Because I know that it's moving along a curve, and number two, I know that ds dt is what? What's ds dt? It's the more technically correct term, not velocity, but it's the speed. It's not the velocity, it's the speed, right? Because velocity is a vector, and ds dt is not. It's distance traveled divided by time is actually your speed. Okay? So instead of using dv dt, we're actually going to use what? Our magical v dv ds. Yes? This is not the first time we're doing this. We've done this in rectilinear. 8a is v dv ds, right? And we did this when we were doing radial. A sub r, what's this? Is equal to v, r double dot is equal to v dv dr, dr, or this is v dv ds. Oh yes, we need to replace ds with a rd theta, right? So this is v dv ds is equal to rd theta. Are you okay with that? Because the distance traveled along the arc is equal to radius of the circle times theta. And now we have a separable differential equation. I'm going to separate it by writing it as gr sine theta d theta, right, equals v dv. Yes, now I can integrate. Okay, from the initial position, when was the initial value of theta? theta is 0 when you're at the vertical position, right? To the final position we're looking for, which is theta max. And what are the corresponding values of the speed on the right side? The initial, I'm going to put v naught, which is 1. 2, what's the final velocity or speed? V at theta max. Okay? Now I'm going to do the integration. What's the integral of gr sine theta d theta? Negative, right? Negative gr cosine theta evaluated from theta equals 0 to theta equals theta max must be equal to, what's the integral of v dv? Okay, v squared over 2 evaluated from v naught to v at theta max. Okay, so I'm going to do the limits. I am going to get rid of the negative sign by inverting the limits, right? So it's going to be g, what? R cosine 0, which is 1 minus cosine theta max. Okay with that? Must be equal to v theta max squared over 2 minus v naught squared over 2. Now, do you recognize this question? This equation? And Nick, of course, recognizes it because he mentioned this earlier. What is this equation? Well, maybe if I cheat a little bit, do that. It's actually your work energy equation, right? So this is your change in kinetic energy, final kinetic energy minus initial kinetic energy. And what do you think is that? mgr1 minus. It's the work done by gravity, right? Because what is r minus r cosine theta max? Yeah, it's actually how much it moves down, right? So this is r cosine theta max, right? Therefore, r minus r cosine theta max is the distance that you moved along the vertical, right? So this is really mg times the change in height, which gives you the work done by gravity, right? Right? Is equal to, so the more convenient way of solving this problem was what? Actually to apply the work energy principle, right? But we're going to call this our third equation, and we're going to combine 1, 2, and 3, right, to solve for what? What are the 3 unknowns here? Oh, actually, I just need, which ones do I need? So I'm just interested in theta max and v theta max. I'm not interested in AT, correct? So I will combine, oh, that was my equation 3. What's my equation 1 here? I'm going to do it along the normal direction, right? Summation forces in the normal direction will give me negative, I'm going to go positive mg cosine theta max, normal is in this direction, must be equal to m v theta max squared over rho. You okay with this equation? Where is this coming from? I'm coming vectors in the normal direction. So mg cosine, oh, is it cosine? Yeah, cosine, because this is theta max here. Where's one theta max? So theta max is the position relative to the vertical. So which one's theta max here? It's this one here, right? That's why it's a cosine. So that's going to be my equation 1. I'm not even going to set up equation 2 along the tangential because I'm not interested in a tangential. So I'll reword this. Just solve 1 and 3. Going to erase that for the two unknowns, theta max and d theta max. But the net conclusion we have is what? This would be easier if we apply the work energy equation. Yes, and the reason was we are looking for a relationship between theta max and d theta max. Right? Over here. And if we learned anything from the first week, we had 3 kinetic principles, right? Newton's second law directly relates forces with acceleration. Work energy relates what? Speed and position with forces, right? And theta is a position. Therefore, if you want a relationship between theta and d, work energy is a more direct way of finding those. And what's the third kinetic principle? Impulse momentum. If you want relationships between forces and which kinetic variables? Velocity and time. Okay? Are you okay with this? Now we're going to go to radial and transverse. So, yes. Mm-hmm. So it depends on which theta you are it depends on where theta is being measured. So if theta in this case is being measured relative to the radial, right? Yes, theta is measured relative to, it's measured with respect to radial. Okay? So the horizontal component will project as a cosine to the radial. Right? So if you're measuring the angle relative to a direction and you're looking for the component along that direction, it's got to be a cosine. Does that help? So for instance here, so here, I'm trying to we all agreed that this was theta max, right? It's angle between the vertical here and the normal line, yes? Yeah, theta is increasing this way. Okay, so if I'm looking for the component of mg in the normal direction, so the theta is actually measured relative to the normal, it's going to be a cosine. Does that make sense? Okay. If I'm looking for the tangential, like over here, right? The theta is measured relative to the normal, not relative to the tangential. If I want the tangential, it's going to be a sine because it's perpendicular to the axis about which you. Of course, if you're still confused, make a really, really huge drawing of the triangle. That's the key. Okay, radial and transverse. So in this case, we do what? Some forces along the radial and some forces along the transverse, and we will end up with 2 equations, right? A radial is of course r double dot minus r theta dot squared, blah blah blah, for a theta So we have two equations, scalar equations, one along the radial saying that summation of forces in the radial is m r double dot minus r theta dot squared, and then summation of force in the transverse equals mass times A transverse, which is r theta double dot plus 2r dot theta dot. Let's look at an example here. The smooth bar rotates in the horizontal plane with a constant angular velocity omega naught. So we're given here theta dot, which is omega naught, and it's constant. Right? So I'm going to define this as my theta, and we are given theta dot equals omega naught equals a constant. Okay? And you agree that in this problem, you have radial and transverse written all over it. Right? You have something that's rotating, and at the same time, probably because of the spring, right, there's a radial force that creates a radial acceleration. The unstretched length of the spring is r naught. So let's call that unstretched length of the spring is r naught. And the color A has a mass of m, and it's released at what? At the position when r is equal to r naught. What do we know? The radial component of the velocity is 0. Yes? I'm just trying to translate this. And what is the radial component of the velocity? Okay, give me the expression for the velocity in terms of radial and transverse. Okay, it's r dot in the E at r, right? Plus r theta dot in the E at theta. Yes? So when it says the radial component of velocity is 0, which one is it talking about? The r dot, right? Yes? Okay, because whether or not we realize, hopefully at this point you realize this thing here is the radial component and this here is the transverse component. Okay? So it's saying that the radial component is 0. The transverse component, of course, is not 0, right? Because r is not 0 and theta dot is not 0. It's constant at omega naught. Okay? So when we're asked to find the radial velocity as a function of position, and letter B, the horizontal transverse force exerted by the bar as a function of r. So we're going to call that force transverse, okay, in the theta direction, as a function of r as well. Yeah? Did I interpret the problem correct so far? Okay, so any suggestions on where I should begin? The what? Radial and transverse vector. So what do you want me to do? Oh, okay. So he wants me to say this is, where's the direction of ER and where's the direction of E at theta. Not a bad idea. And then what? Figure out which radial loss. How would I do that? Okay, so he's suggesting free body diagram. Would you like me to look at the free body diagram? I know at least that the F theta will show up in the free body diagram, yes? And number 2, this topic is on chapter 12, Newton's second law, right? Okay, probably free body diagram, yes? Okay? Are we okay? So I'm going to look at what? The FBD of the color at some arbitrary position, at some arbitrary theta and some arbitrary r. Okay, so what are the positions, let's say it's this positioning. What are the forces acting on the color? So I'm looking at the free body diagram of the color, right? What are the forces acting on the color? Gravity, Okay, so how do I show the gravity here? Is gravity going to say? Usually it does, right? Read the problem carefully. So it rotates in the horizontal plane. So this view that we're looking at here is actually the top view of the picture. You agree? Yeah, so the gravity is actually going into the page, right? Okay, because this is the horizontal plane according to that. Yes. So gravity is not to be shown. If you want to show it, it's going to be into the page, and that gravity force is always being balanced by some normal force coming from the bar. It doesn't affect the motion, right? Because it doesn't accelerate in the z direction. It always stays in the same xy plane. So there must be no net force in the z direction. So we don't have to show gravity. Yes? Are you okay? Okay, so what else did you say? Force from the spring, right? So I'm going to assume here that at this position R, okay, that I'm showing, it's bigger than the undeformed length of the spring, so it's stretched. Okay? So in that case, what's the direction of the force of the spring? Towards the origin, and we're going to call that F sub, E for a spring, right? I am assuming this. R is variable. I can assume it at a smaller R than L naught. Okay, I just want to make my assumption consistent with the picture. If I assume R is less than L naught, the spring is actually compressed. Fe would be to the right. Okay? And I want this at any variable R. Anyway, right? So I just took one case. Okay? And what's the force of the spring in this case? It's going to be K times, okay, you call it X, okay, but what would be, it would be R? Would it be R? It's R minus R naught, right? Yes. X is the deformation of the spring away from its undeformed length. If its undeformed length is L naught and the actual instantaneous length is R, it's stretched by that amount, okay? Okay, what other forces are acting in addition to this? Yes. Which one? No, because it should be R, not R dot. R minus R naught is... Yeah, so you have to be careful. If you say that delta R is equal to, you're saying delta R is equal to R dot times delta T, right? And this R minus R naught is with respect to position, but it's also changing with respect to time. You can, but you're going to be invoking another variable, which is time. Okay, I'll just leave it as R because it's okay to leave R because we're expecting an answer that's in terms of R, not in terms of time. Yeah, if it wants you to express it in terms of time, yes. Okay, but I will also be hesitant because this is delta R, not dr. Okay, so if the R dot is not constant, right, what you're saying is not true. Yes? Okay. Okay, so must be equal to what other forces are acting on this? Is it touching anything else? Nope, there's no friction. There is another normal force, right? There's a normal force opposing gravity, right? But there's also another. We don't want to call it normal. It's actually what? In the transverse direction. Yes. Coming from the bar. Yes. And in fact, that's what we're at the point here. Where is it? Where is it? Here. Oh, here. Oh, here. Right? Okay. So think free body diagram again. How do you know what forces to show? Gravity generally doesn't need contact. Everything else needs contact. So all you have to do is, what other things are touching my collar? The spring is touching the collar. That's why you have the force of the spring. And the bar is touching the collar. And the forces of the bar on the collar actually has two components, right? One in the vertical and one perpendicular to the bar in the horizontal. There's no force in the radial direction because there's no friction. It's free to slide along the bar. Yes. Are we okay with the free body diagram on the left? Okay, on the right, what do we need to show? A mass times acceleration radial, and a mass times acceleration transverse. Okay, and we are interested in what? R dot and theta. So let's see. The R dot here, I can actually express as what? R double dot minus R theta dot squared, okay, whereas the A theta here can be expressed as what? R theta double dot plus 2R2 toilet bowl, R dot theta dot, okay. Now let's decide which ones of these we know already. Do we know any of these? Okay, we know that theta dot is omega naught. Okay, so this one's done with. And R is fine. We don't know R, but we want an answer in terms of R. So I'm going to leave R there. Okay, so it's R double dot that we don't know. On the second one, we know theta double dot also to be 0. Right? So it looks like the unknowns are R dot over here. Yes. And R double dot over here. Okay? So, is this a happy system? How many unknowns do I have? So I have 2 on the right side. However, I have an F theta on the left side. Yes? Okay? And do you agree? This is the only free body diagram that I can use. There's no other free body diagrams I can look at. Okay? Which means that I may need another equation, but that equation is not a free body diagram. That equation will use a piece of information that's given somewhere. What piece of information have we not used? Nope, we've used that. We're going to use that here. What piece of information? Right, there's no radial velocity when R dot is 0 when R equals R naught, which does not necessarily substitute into this being 0, right? R dot is not 0 necessarily. It's only 0 at this initial condition. That's why I didn't count R dot being 0. Okay? It's only 0 at R equals R naught, but this is at some arbitrary R bigger than R naught. Yes. Okay. So I'm going to set up the equations now along the trans. Let's go to the radial. So what would be my equation along radial? Summation of forces in the radial direction. What would I get? Negative K r minus r naught. Yes, it's negative, right? Because radial is outward. Must be equal to, what would I have along the radial direction here? It's going to be m r double dot minus r. Take the dot squared. I'm going to replace that with omega naught squared. Are you okay with that? Okay. And my second equation, if I sum forces in the transverse direction, would give me what? F theta. That's the only force in the transverse direction. What would be my, oops, what just happened? M times what? R times theta double dot, which is 0. So I'm going to put 0. Yes. Plus toilet bowl effect, which is 2r dot theta dot. Okay, let's do omega. Thank you. So the second one here, which will give us directly f theta, we are done with, provided we know what r dot was. Yes. And that's really what part A of the problem is, right? V sub r of r is really, do you agree? This is r dot as a function of r. Yes? Yes? Okay, so if I answer part A to find r dot, I'm pretty much home. I just substitute r dot here and I'll find f theta. Okay? So what that means is I'm going to look at the first radial equation. Let me rewrite that as minus k r minus r naught is equal to m times, what was it? R double dot minus r omega naught squared. Okay? Now we're asked to solve for VR. Yes, which is, what is that? R dot. Okay, so I'm going to rewrite the right side as, what is r dot? R double dot. That's the same as the derivative with respect to time of r dot, which is VR. Yes. Are we okay? I'm not doing magic here. I'm just expressing r dot in terms of VR because the question asks us for what VR is. Yes? Are you okay with what I've done here? Yes or no? Okay. So what do I have here? Remember, I'm looking for VR. So we see a differential equation. Yes, because VR only appears as a derivative. However, is this a separable differential equation? Why not? Yeah, we have three variables, right? R, VR, and T. Yes? And which one of these three variables are we not really interested in? T. So I need to eliminate T. How would I eliminate T? Okay, I'm going to use the fact that dVr dt, it could be written as dVr. What variable would I use instead of, oops, not S, because it's R. It's got to be R, because the only other variable we're allowed to keep is R. Times what? dr dt. So what is dr dt? What is this? Which is VR, right? So again, we see this. R double dot could be replaced by VDV VR. And again, this is not the first time we've seen it. Whenever you try to eliminate time, it's always going to be speed, dB, speed, D speed, T position. Whether it's S, if you're in normal tangential, or X if you are in rectilinear. Yes, this is like A is V dV dx, and like A tangential was what? VDBDS earlier, right? Still the same thing. Okay. So what do we have now is K R minus R naught equals M VR dVR dr minus mr omega naught squared. I'm attempting to separate now. So what do I need to do? I need to move everything that has an r on the left side. Yes? Now, does it look like it's separable? So how do I separate? I'll just multiply everything by dr. Yes? It's going to be K R minus R naught plus mr omega naught squared dr equals n dr dvr. Now I'm ready to integrate. What are the limits for r? I left the integration with respect to r. We have given initial conditions, right? When r was r naught, br is 0. Yes, so my limits would be when r is r naught, what is our br? Is 0, right? And let's give your Calc 1 teacher a heart attack. When r equals r, br was br. No dummy variables, right? Only dummy people would use dummy variables. So let's integrate the first one. What's the integral of k r naught, r minus r naught? R minus R naught squared over 2, square that, plus, what's the integral of mr omega naught squared? M is a constant, omega naught squared is a constant, would be r squared over 2, evaluated from r naught to r, must be equal to, on the right side, integral of VR dVR is VR squared over 2. Yes, evaluated from 0 to VR. So what would I get here? What would be our VR? Let's do a shortcut. So I multiply everything by 2, right? Divide everything by m, and then take the square root. So it's going to be plus or minus the square root of, doing my algebra sort of test. So the left side would be, when r equals r, I'm going to have a k over m, right? R minus r naught squared, that's at the upper limit. The second term will be m over m will cancel, right? It will just be omega naught squared, r naught squared. The 2 is gone. And at the lower limit, it would be minus. The first term is going to 0, because r equals r naught. And then the second term will be equal to, whoops, this one's wrong. What's wrong? This doesn't have an r naught. Yes. This one here has an r naught. Yes? Did I do that correctly? And once I have VR, so that's done. So by the way, why do we have a plus or minus? Algebra says when you take the square, it's a plus or minus. But in this case here, the problem that we're looking at, why do we have sometimes VR plus, sometimes VR minus for the same position R? Yeah, because of the spring. As this thing rotates counterclockwise, the spring actually makes the color oscillate back and forth along its length. So for the same position, when it's moving outward, VR is positive. For the same position in its return, for the same position R when moving inward, VR is minus. Okay. Then once we have VR, what do we need to do now? Just substitute the VR here. We'll give you what F theta is. Okay. Oops. Let's stop here. Like, oh, I didn't really notice that it's time. So hopefully you guys can attend the ship meeting today. And I